this class with FDM and TDM systems. Okay, so this is one leftover topic in our syllabus, and there is one more, two more leftover topics like QAM and DPCM. So I'll cover those two topics in the next class. So with that, I'm going to finish the syllabus. Okay. So today's our topic of discussion is FDM and TDM systems. Okay, we know well about FDM and TDM. Okay, and now and then, here and there, I discussed about FDM and TDM. So when I was teaching about modulation processes and here and there, I talked about FDM and TDM. Anyway, so let me talk about right now also FDM and TDM. Okay, so what it means FDM? First we take up FDM and TDM. Okay, first of all, let me say multiplexing. Okay, because these two, FDM and TDM, are actually two multiplexing techniques which are used to send the signals, a number of signals on a single common channel. Okay, so first of all, what is multiplexing? Okay, this is a already well-known term to us. Okay, multiplex. Okay, multiplex means many to one, many to one. Okay, so many to one, many in one, like that. Okay, as far as the communication is concerned, what it means multiplexing: sending, transmitting several number of message signals on a single common channel. Okay, so that can be done by using either of two techniques known as FDM and TDM. Okay, so multiplexing means sending number of message or information bearing signals on a common single channel or single carrier. Okay, now there are two techniques. Okay? One is FDM and other is TDM. Okay, what do you mean FDM? FDM means frequency division multiplexing. Okay, similarly TDM means time division multiplexing. Okay, once again let me say about this multiplexing. Multiplexing means sending number of message signals on a common single channel. Okay, that can be done either by frequency division basis or time division basis, frequency sharing basis or time sharing basis. Okay, so now let us talk about a little bit more about FDM. Okay, as I said, in frequency division multiplexing, number of message signals are transmitted on frequency division basis or frequency sharing basis. This means given frequency range or band is divided among number of message signals. Okay, that means if there are 10 number of message signals and all those 10 number of message signals have to be transmitted on a common single channel, then a given frequency band is divided among those 10 frequency band. That means given frequency band is divided into or split into 10 small frequency bands, and each and every frequency band is allotted for transmitting one particular signal. Okay, so that means if there is a frequency band, let us say this is the frequency band that we have. Okay, this frequency band divided into number of small subbands. So this is one subband, this is another subband. Okay, this is another subband, like that. This is first subband, second subband, third subband, and so forth. This is nth subband. So given frequency band divided into number of subbands, and each and every subband is used for one particular signal. So this is meant for transmitting first message signal, and this is for second message signal, and this is for third message signal, and so forth. This is for nth message signal. Okay. So like that, given frequency band is shared among the signals. So this is called a frequency division multiplexing, isn't it? Now, let me take a simple example to understand a little bit more. Okay. So there is a frequency band or range, frequency range from 900 kilohertz to 1000 kilohertz. Okay. Now I want to use this frequency band to send 10 message signals. Okay. Message signals. Each one, okay, each having a band of 10 kilohertz. 10 kilohertz. Then what I need to do? I need to divide. How much is the band here? From 900 kilohertz to 1000 kilohertz, we have 100 kilohertz band. This 100 kilohertz band is divided into how many subbands? That depends upon how many number of signals you are supposed to transmit. You need to transmit how many? 10. So that's why we need to divide 100 kilohertz into 10 subbands. 10 subbands. Okay. Each one is how much? 10 kilohertz. Okay. So if that is the case, the first subband will occupy from 900 to 910 kilohertz. And the second subband will occupy from 910 kilohertz to 920 kilohertz. And so forth. So finally, the last one will occupy a frequency band of 990 kilohertz to 1000 kilohertz. Like that, each and every subband which is having 10 kilohertz is allotted to one particular signal which is having 10 kilohertz, isn't it? Okay. But basically, all the message signals will be occupying the same frequency band. For example, if you take a audio signal, that audio signal will range from 0 to, theoretically, 0 to 5 kilohertz or 10 kilohertz or 15 kilohertz, depending upon the type of transmission we are using, whether FM or AM, like that. Okay. So let us say the audio signal is ranging from 0 to 10 kilohertz. All audio signals, that means all 10 message signals, that is all 10 message means 10 audio signals will occupy the same frequency band. Then how to get into these bands? You need to frequency translate each and every message signal to the corresponding subband. Then we can combine to form a frequency division multiplexer signal. Okay, you get the point. Okay. So first, what you need to do, all message signals have to be frequency translated by using some other means, frequency translated to the desired subbands, and then all those subbands are combined to form multiplexer signal. Okay. Okay. Now let me show more clearly by taking an FDM system. Okay. So FDM system means frequency division multiplexer system. Okay. In which the message signals are transmitted by performing frequency division multiplexing, and at the receiver it is demultiplexed to get back the original signals, isn't it? So let me show that one. In this FDM system, this is the transmitter. This is the transmitter. Okay. Here in this transmitter, no, at each and every location, You see, if it, this is the input, one input, this is another input, this is nth input. Like that, there are number of inputs. Okay. So let us see how these signals are frequency division multiplexed. Okay. So this is message signal 1. Okay. And this message signal is allowed to pass through low pass filter. Okay. Because all message signals must be first band limited. So how can we band limit a signal? Just by passing the signals through low pass filters. Okay. So the first message signal after passing through the low pass filter, you know, it is band limited to W hertz, isn't it? And then that signal must be frequency translated to a particular frequency subband. How that can be done? By using one type of modulation. So here we are taking SSB modulation, single sideband modulation. In this single sideband modulation also, we are taking upper sideband. We are considering only upper sideband. This is upper sideband single sideband modulator. Okay. So the output of SSB modulator, he is an SSB signal with upper sideband. Okay. If that is the case, and for this SSB modulator, the first carrier frequency is how much? F1. That means the first message signal after band limiting is used to SSB modulate carrier, subcarrier F1. So the output will be a frequency translated version. Okay, frequency translated version, that is SSB modulated signal with upper sideband, is simply called a frequency translated version. To which frequency? F1. Okay. So before SSB modulation, the signal is having a frequency from 0 to W. After SSB modulation, it is ranging from F1 to F1 plus W. So this is about the first message signal. In the same way, each and every message signal must be first band limited and then use it to SSB modulate the respective corresponding subcarriers. Okay, to get the respective frequency translated signals. Okay. Second message signal, the corresponding band limited and then corresponding frequency translated version. Okay. The same way, nth signal corresponding and corresponding frequency translated versions. You see, have you seen all these are having a different frequency bands. This is from F1 to F1 plus W, and this one is from F2 to F2 plus W, and this is Fn plus M. That means, but before SSB modulation, all these are having the same frequency band. So these frequency bands are shifted to different ranges by performing this modulation. That's why one of the need of modulation is frequency division multiplication. Okay, just to remember, one of the needs of modulation is frequency division multiplexing. Here we are, what we are doing in this frequency division multiplexing, we are making use of modulation to achieve the goal, to achieve the aim. Okay, so each and every message signal is shifted to a different frequency range. Okay, here it is F1 and here it is F2 and here is Fn. Okay, after this, all these signals, frequency translated signals, are added. Okay, after adding, what will happen? If you add the message signal right here without performing any modulation, what will happen? All these will merge, all will overlap. That means the signal will be distorted. But here, after performing modulation, they have shifted to different frequency ranges. So if you add them, then what will happen? They will not overlap, because here that also depends on the frequencies F1, F2 and Fn. Okay, here if you choose these frequencies, subcarrier frequencies, so that they are different frequency range by an amount of bandwidth W, they will not overlap. And if you take more, what will happen? Then also they will not overlap, but there will be some gap between these frequency bands. No, if you take the difference between subcarrier frequencies more than W hertz, what will happen then? Then there will be more amount of gap between the subsequent bands. Nothing wrong will happen. Okay. Anyway, so here if you take the subcarriers F1, F2 and Fn, so that the difference between them is around W hertz. After combining them, you'll get a signal like this. So this signal is called frequency division multiplexer signal. You see, here all are actually multiplexed. They are placed side by side with the different bands. Okay, so a given band from F1 to Fn plus W is divided among n number of message signals. Okay, so this is called simply a frequency division multiplexer signal. Okay, and after having a frequency division multiplexer signal, we need to transmit over the channel. So before transmitting over the channel, we need to perform once again a carrier modulation. Okay, this whatever the carrier that is used at this stage is called a main carrier. Here the main carrier is Fn or Fc. We can use it Fc, not Fn. This is a Fc. Okay, some higher frequency component compared to all this. So after modulating this TDM signal over a main carrier frequency, will be getting an FDM FDM signal, FDM RF signal, FDM RF. Okay, now so this is after performing carrier modulation once again with some carrier Fc. So what will happen? This entire frequency here also I'm taking upper side band. Then what will happen? You see, because of this carrier frequency Fc, all these will be shifted to Fc plus. Okay. Here we have to remember one thing. Okay. All input signals are simultaneously band limited and simultaneously modulated their subcarriers and then added. Okay. That means all the signals are transmitting all the time. Okay. All these message signals are transmitted all the time. Okay. But they will occupy different frequency bands. Let me show that. You see, all these message signals are applied simultaneously to the low pass filters, and then simultaneously they are band limited and simultaneously frequency translated to their respective subcarriers or subband frequencies, and after that they're added. Okay, after adding, it is used to modulate once again the main carrier before transmission. Okay, so this is finally an FDM signal which is ready for the transmission. Okay, so this is entirely an FDM transmitter. Okay, now we see receiving end. At the receiving end, what will happen? You see, so this is the received signal, no doubt. Okay, the received signal is having again n number of message signals occupying different frequency bands. Okay, so first we need to down convert it. Okay, that's why we are using a local main carrier whose frequency is Fc. Okay, here we can use what we call coherent detection. We can use coherent detection to demodulate this. So after demodulation, what we can have? We can have demodulated signal, which is a time division multiplexer, frequency division multiplexer signal. Okay, so which is ranging from F1 to Fn plus W hertz. Okay, and the same signal is applied to a bank or a set of n number of band pass filters. Okay, we have here n number of band pass filters. Each one is tuned to a different center frequency. Here, the first one is tuned to F1, the second one is tuned to F2, and the last one is tuned to Fn. So when the first one is tuned to F1 means what? It will send only a band of frequencies around F1. Okay, isn't it? So the first band pass filter will allow only the first message signal, first band signal. First band signal is from F1 to F2. Similarly, the second one will allow only the second band. Finally, the last one will allow only the last band, isn't it? So the input to all these a set of band pass filters is same, but depending upon the frequencies to which the band pass filters are tuned, they will allow the respective bands. Okay, so what will happen now? Output of the first one will be this one. Okay, you see here, output of the band pass filters will be like this: F1 to F1 plus W and F2 plus F2 to F2 plus W, like that. At the output of each and every band pass filter will be having the corresponding subband message signals. Okay, so after that, each one is demodulated by corresponding the local carrier. So the first one, the first band of frequencies from F1 to F1 plus W is a modulated, used to modulate local carrier whose frequency is F1. So then what will happen to the output? You see, the output will be 0 to WHz. Before this, they will be having some higher frequencies. After passing through low pass filter, it is limited to WHz. Okay, so like that, at the output of each and every low pass filter, we'll be having again the same message signals which are generated from the sources. Okay, isn't it? So this is how you can send number of signals by using frequency division multiplexing system or multiplexing process. Okay, you see here we are using a single carrier. All this multiple signal is transmitted through a single channel and a single carrier, that is a main carrier. Okay, that's why we are calling it as a multiplexing. Okay, next one. Let us come back to okay. So this is about a FDM system. Now we talk about TDM system. Okay, TDM, time division multiplexer system. TDM. Sorry.
Sir.
Now can you see the board?
Yes, sir.
Okay. So now let me continue with the TDM. So TDM means time division multiplexing. So what it means? Here also the same way how we are transmitting number of message signals in FDM. Here also we transmit number of message signals by using a common single channel. But what the principle that is used here means time sharing. Okay, time sharing. Here, the given frame time is used, or given frame time is divided into small time slots. Okay, and each and every time slot is used for transmitting one particular signal. Okay, did you get the point? So, given frame time is divided into smaller so we divide given frame time into number of smaller time slots. Okay, so it is 1, 2, 3 like that. So we divide into a number of, and each and every time slot is used to transmit one particular signal. Okay, one particular signal. For example, if I want to transmit once again n number of message signals by using time sharing basis, we need to take some given frame time. So in that frame time, we need to transmit each and every signal, like taking a particular time slot. Okay. For example, let me explain. For example, I want to transmit 10 number of message signals. Okay, each is having 5 kilohertz. Okay. Then what about before transmission here, we need to perform sampling because we are sending all the signals, not all the time. So we are sending only the signals for small intervals of time. That means we need to sample. So that's why the sampling frequency is 2 times of bandwidth. So it is 2 into 5 kilohertz. Okay. It is simply 10 kilohertz. Then what about the time, sampling time 1 by fs, that is 1 by 10 kilohertz, simply equal to how much? Point, that means 100 microseconds. Okay, 100 microseconds. Okay. So now this 100 microseconds is a frame time. So we use this 100 microseconds as a frame time to transmit the samples from each and every 10 number of message signals. Okay. So we need to divide this 100 microseconds, that is from 0 to 100 microseconds, is divided into how many time slots? 10 time slots. So first time slot, second, third, and so on. So this is the first time slot. 0 to how much? 0 to 10 microseconds, 20 microseconds, 30 microseconds, and so on. Finally, it is 90 microseconds. Okay. So during the time interval from 0 to 10 microseconds, the first signal is transmitted. Okay. During the time between 10 microseconds to 20 microseconds, second signal is transmitted. Okay. So during the time interval from 0 to 10 microseconds, the first signal is transmitted. During the time interval from 10 microseconds to 20 microseconds, the second signal is transmitted. Like that, each and every message signal is transmitted during the time intervals which are confined to them. Okay. So finally, the last one is transmitted between the time interval from 10 microseconds to 100 microseconds. Okay. So like that, all the message signal, I mean the samples from this is about one frame time, that is 0 to 100 microseconds. Like that, we'll be having one more, the next frame time. Like that, during each and every frame time, the samples from the corresponding message signals are transmitted during their respective allotted time intervals or time slots. Okay. So this is about a TDM system. Okay. So that means here we are transmitting message signals based on time sharing basis. So given frame time is used by all the message signals. Okay. Now let me show the diagram. Let me show the diagram here. See, so this is TDM system. Okay, TDM system means a system in which number of message signals are transmitted based on time division multiplexing method. Okay, so that means time sharing basis. If you send a number of signals to a common single channel, we call it as a time division multiplexing system. Okay, you see in this all the message signals, M1, M2, and Mn are low pass filter. Okay, low pass filter to the same bandwidth, and all these are applied to a commutator. So commutator is nothing but a simple rotary switch. As the switch is rotating, it is connected to the modulator. Okay, when it is connecting, the first one, it is said to be taking the sample of the first signal. Okay, and when it is connected to the second signal, it is taking the sample of the second signal. While it is taking the sample of the second signal, okay, the other signals are not connected anyway to the pulse modulator. So at any one point of time, only one signal is connected. One signal sample is transmitted. Okay, isn't it? So not all the signals as in case of FDM. In FDM, all the signals are transmitted all the time, but they differ in only frequency bands. But here in TDM, all the signals will not be transmitted simultaneously. They are transmitted on time sharing basis. That's why at any point of time, only one signal is transmitted while others are not transmitting. Okay, that means all are occupying the same band. All are occupying the same band. Okay, that means bandwidth is same. Okay, so when this rotary switch is connecting each and every signal, that corresponding samples are connected to the pulse modulator. Okay, so and after modulation, what will happen? It is sent to the receiver. Okay, sent to the receiver. Let me show the receiver also. So this is the receiver. Okay. See, now this is entirely a TDM system. Okay. Here we have a commutator and a decommutator. These two are very, very important. Okay. So when you talk about the commutator, it performs two functions. One it is sampling each and every signal, and then it is interleaving those samples. Okay. Sequentially, all those samples are interleaved by this commutator. Okay. It is sampling and then interleaving those samples to form a sequence of samples, isn't it? Okay. The commutator exactly performs the reverse operation. Okay. So if you look at the entire TDM system, when the commutator is connecting to M1, here this decommutator is connecting to M1 here. Okay. And if the commutator is connecting to M2, at the time what sample is transmitted? The samples corresponding to M2 is connected. It is modulated and sent to the demodulator. I mean, through the channel it is sent, and at the receiver, this is the receiver part, So at the front end of the receiver, we have a demodulator. It will actually get back its sample, and that sample, should be connected to the upper low pass filter in order to get it as M1. That's why the commutator and decommutator will operate in synchronization. What do you mean in synchronization? When the commutator is connecting to M1, here also decommutator has to connect to M1. So whatever the sample you are getting when the commutator is connecting to M1 corresponds to M1 only. That's why the decommutator also has to connect to M1. So like that,